Good evening, everyone. My name is Ritam Agarwal, and I have Aviral, Jason, and Brian as my teammates who have worked together on this project. Our group will be presenting the machine learning project for the American Express Default Prediction Challenge. This is next one. This is the content overview and the flow of our today's presentation, where we make you go through the introduction, the problem statement, how we proceeded with the exploratory data analysis, the modeling approach and the models used, the data preprocessing, model training, results and comparison, and finally the conclusion. American Express currently has over 118 million cards in circulation worldwide. And understanding which customers are at risk of defaulting is crucial for managing financial stability and minimizing losses. This project aims to address that real world challenge through data driven modeling. The core problem we were tasked with was to predict whether a customer will default on the credit card payments or not, based on a wide range of anonymized financial and behavioral features. Because the dataset is large, high dimensional, and heavily imbalanced, choosing the right preprocessing approach and modeling techniques is essential. Our goal was to build efficient models that can accurately learn these patterns and generalize well on unseen customers. I shall now pass my time to Brian, who will make us go through the EDA process.
All right, sure. So first off, we made use of a Kaggle notebook to actually make use of the code for the Kaggle competition. So using Kaggle, actually, we managed to perform EDA on our data set. So actually, here is a brief overview of the matrix that we used for the data set, which are namely the positive clients, the statement count, the categorical features, the numerical data, as well as the histogram data. So first off, we will have a look at the data types available. So you can observe that out of the 190 columns detected, 185, which are the majority, is actually float 64 data type. Then 4 of them are actually object column types, and 1 of them is lastly the integer 64 data types. So the row entries in total, there is about 5,531,451 rows, of which there's 458,913 distinct customers. So the next few slides will help us to better understand the data, and we can see how it helps our model. So first off, we can see the majority of the customers actually do not default on payment. So we can see that we can also see that out of the distinct 400,000 plus clients, there is a mean statement count of 12.05 and a median count of 13. So next, we can also explore the categorical features of some of our values. So for D63, we can see the majority of the rows falls under the CO, charge off, and CR credit, taking up the majority of the entries. For D64, we can see the majority of the rows fall under the U and the O categories. So next, out of the data types that we have, there are also several numerical float data types. So you can see that actually for P2 as well as S3, they're actually both heavily skewed towards the polar ends, which indicate that actually the data set is actually quite on the polar opposites. So lastly, we can also make use of histogram to find out if there's any correlation between any of the data. So through the plot, we can see that the highest correlated data columns are actually B4 with B7 as well as B6 with B10. However, we can see that the rest of the data types are actually not really correlated at all. So through this EDA, we can now have an in-depth analysis of the data set provided with which shows that actually there's a huge data variance that is very longitudinal in size with a high sparsity and huge imbalance in data. There are also many time-varying features in the data set. Next, I'll pass the time on to Jason to share more about the modeling approach for our training process.
I will now explain the modeling approach for the problem. The nature of the dataset, as we just discussed, creates some certain constraints that limit the choice of model. First of all, the volume of the data will limit our approach. Whatever model we use must be scalable and able to train on the compressed data. Since features are anonymous, domain knowledge cannot be used, and relationships must be determined automatically. And the high amount of dimensions could also cause overfitting if regularization is not applied. So with these constraints, linear models like logistic regression will be ineffective because of nonlinear relationships. Neural networks will require extra data processing to handle the missing entries, as well as taking longer to train. Given these factors, we decided to focus on decision tree-based models to perform the task. The two models we used are random forest and LightGBM. Random forest is a simple, robust model that performs well with minimal tuning, so this can serve as the initial benchmark to compare future models to. Meanwhile, LightGBM can natively handle missing values, supports categorical splitting, and can scale well to the size and the structure of the dataset, so it should be able to capture patterns with more detail and provide a better performance. I will now explain the data pre-processing and what steps we took to prepare the data for the model. The main challenge for us to address was the large size of the dataset. With 17 gigabytes of training data, some processing will be required to reduce memory usage and training time. Otherwise, running out of RAM mid-execution is a real possibility. Aviral will now elaborate on our solutions to address the issue.
Given the large data set size, a full aggregation of every row would easily overload the notebook. So we designed a unique two-pass pre-processing pipeline to make the data tractable. First, we scan only the customer ID and the S2 timestamp columns to find the latest statement date for every customer. Then, in the second pass, we only keep rows that correspond to that last date. So each customer is represented by exactly one final state row. This preserves the most recent financial behavior, which is the most relevant for default prediction, while reducing the data set from millions of rows down to something trainable. For categorical features like D63 and D64, instead of one hot encoding, we use hash encoding, which compresses them and into low-light integer codes, and this prevents future feature explosion and ensures both train and test data use the same consistent encoding. After these steps, our process tables fit comfortably in memory and can be used directly by both the models. After pre-processing, we merged the final per customer features with the target label and performed an 80 by 20 train validation split. We fixed the random seed, so both random forest and light GBM were trained on the exact same data partitions, ensuring a fair comparison. We chose not to use a k-fault cross-validation because of the dataset size and runtime limitations. However, the validation set is large enough to give a suitable estimate under the AMX metrics. Okay, over to Jason, who will explain random forest.
Here's a brief explanation of how we implemented the random forest. First of all, some extra steps were taken to reduce data size. Certain features were able to have the storage size reduced through downcasting, for example, converting int64 into int8. We also cached the data using Parquet, a file type designed for greater efficiency and data compression. The model itself is a random forest classifier with optimized hyperparameters aimed to balance complexity, computation cost, and generalization, and the parameters we use are listed to the right. The model was trained with CPU-parallelized random forest with stratified sampling and balanced class weights, meant to improve minority class recall and prevent overfitting. Aviral will explain light GBM now.
Okay, so our second model is light GBM. Right, our second model is light GPM. We train the model on GPU and use a tuned set of hyperparameters, including number of leaves and feature fraction, and L1 N2 regularization. We also used early stopping to prevent overfitting and implemented the official AMX competition metric as a custom callback during validation. Feature importance analysis also showed that the model was able to pull out meaningful patterns from features like B11, D39, R1 that random forest could not capture as effectively. Over to Rhythm.
After training and evaluating both our models, Random Forest and Light GBM, we observe a clear performance difference. Random Forest served as a strong baseline, but it struggled with the dataset scale and the complex non-linear linear relationships present in over 180 features. Light GBM, on the other hand, consistently delivered better results. Its ability to handle missing values natively, use leaf-wise growth, and leverage GPU acceleration allowed it to capture subtle patterns in the customer data more effectively. This resulted in strong performance on both the ROC, AUC, and AMX competition metric. In conclusion, our findings show that light GBM is far more suited for large, high-dimensional financial datasets. Its speed, efficiency, and predictive power make it an excellent choice for organizations like American Express that rely on fast and accurate risk assessment. Ultimately, the project highlights how meaningful model selection and careful data pre-processing can significantly improve real-world decision-making.